Chemistry, the Central Science, Chapter 5, Thermochemistry, Lesson 2. So in the last lesson, we were introduced to the concept of enthalpy, which enthalpy is heat transferred under constant pressure. So most reactions that we talk about, we can just talk about the enthalpy for those reactions because we see that very little work would potentially be done because there's an extremely small amount of volume change. So when we're given enthalpies of reaction, how can we manipulate the equations based on what we have? So for example, in line 1, we have the melting of water going from solid water to liquid water. It is endothermic because we see that the sign is positive here. So this is the amount of energy required for 1 mole. Well, what happens if instead we want to freeze water? We want to go from the liquid state to the solid state. So all we've done is reverse the reaction, which then means that we reverse the sign of the enthalpy. So for a forward reaction, in this example, it's positive. For the reverse reaction, it's negative. Remember that anytime we are freezing something, heat has to be given off. So this is exothermic. So what if instead of wanting to do 1 mole of water, we want to do 2? Well, then all you have to do is multiply your enthalpy by the coefficient in which we've changed. So we would need double the amount of energy to be absorbed if we wanted to double the amount of water that we were trying to melt. So once again, line 4 is just like line 1, but it's just to compare here between, or paying attention to the fact that states do matter. So solids, liquids, and gases. We can see here that if we wanted to evaporate water, we were going to boil it. It requires a significantly more amount of energy to do that process. And then just keep in mind, right, if instead we were going to condense this, we were going to go from a gas to a liquid, the same amount of energy is associated with the process, but the sign would become negative. So then we'd have to give off 44.0 kilojoules of heat. So practicing with enthalpies of reaction. We have the reaction of nitrogen monoxide combusting to form nitrogen dioxide. The enthalpy that is associated with this reaction is negative 114.6 kilojoules per mole. So this means per mole of the reaction. Is this exothermic or endothermic? Well, when we answer the question, all we're doing here is looking at the sign. The sign is negative, so we know it's exothermic. What is the enthalpy change per mole of NO2? Well, here we see that it's for 2 moles gives us this energy. So we would do a conversion that says for 1 mole of the reaction, this is the enthalpy. And there are 2 moles of nitrogen dioxide in the equation. So we simply divide our enthalpy by 2 and see that for every 1 mole of NO2, the enthalpy associated with that is negative 57.3 kilojoules per mole. So we've halved it. How much heat is produced when 1.26 times 10 to the 4th grams of nitrogen dioxide are produced? We always keep in mind that anytime we're given mass or molarity or anything like that, we always have to get to a number of moles so that we can then use our equation. So we have to find the molar mass of nitrogen dioxide. We look at our periodic table. 1 nitrogen plus 2 oxygens gives us 45.9947 grams per mole. Grams are here, grams are here. We have to cancel that out. Remember, for molar mass, it's always 1 mole. It has nothing to do with the balanced equation. Then our next step is to look at the balanced equation and see how many moles of nitrogen dioxide are in the reaction. So 2 moles per every 1 mole of reaction that we do. And the enthalpy associated then with 1 mole of that reaction is our given value of negative 114.6. So we do our unit conversions here. We multiply everything together on the top. We divide by everything multiplied together on the bottom, canceling out the units as we go along to see that we end up with negative 15,700 kilojoules. So this is the amount of heat that is produced if we want to make 1.26 times 10 to the 4th grams of nitrogen dioxide. We can perform similar calculations if we were given a mass of NO or a mass of O2. How many grams of nitrogen dioxide are produced during an enthalpy change of negative 3,790 kilojoules? So now we have an amount of energy that we're going to produce. We want to know how many grams that we can get. So once again, we're setting up a conversion. We start with our given information, and we recognize that for the reaction, negative 114.6 kilojoules are released for every 1 mole of the reaction that we do. Once again, we look at our balanced equation. We see that there's 2 moles of NO2 for every 1 mole of the reaction, and then we multiply by our molar mass to go from moles to grams. Canceling out our terms as we go along, multiply everything together on the top, divided by everything multiplied together on the bottom. We see that we get 3,042 grams of nitrogen dioxide produced if this is the amount of heat liberated in the reaction. So when you're using enthalpies of reaction, we can either determine an amount of product or an amount of reactant in terms of grams, or we can find the amount of heat associated with a particular reaction if we're given so many grams of a substance. So specific heat capacity. The specific heat, by definition, is the amount of heat required to raise 1 gram of a substance by 1 degree Celsius or 1 Kelvin. And we keep in mind that the Celsius temperature scale and the Kelvin temperature scale changes by the same amount. So 1 degree Celsius change is the same as a 1 Kelvin change in temperature. The molar heat capacity is given in units of joules per mole. So how much energy per mole of something is required for a particular temperature change. So if you wanted to convert between specific heat and molar heat capacity, we keep in mind that one has units of grams and one has units of moles. And all you have to know then is the molar mass. So if we wanted to go from specific heat to a molar heat capacity, we would be multiplying by the molar mass, and just vice versa. If we were given molar heat and we wanted to figure out what the specific heat was, instead we would be dividing by the molar mass. So heat, which we've talked about, which is not a state function, can be calculated by looking at the mass times the specific heat times the temperature change. Or we can look at a molar heat capacity and simply multiply that by a temperature change if we wanted heat per mole. So keep in mind here, the units would come out to be joules. Down here, our units would come out to be joules per mole for a particular reaction. So there's a table in your book that lists some specific heats as well. And how do we utilize this table? Well, it's applicable or practical to look at, say, copper and iron, right? You go to the store, you're trying to figure out, do you want to buy a copper skillet or do you want to buy an iron skillet? So what these numbers tell us is, right, we see that the specific heat for copper is lower than that of iron. So what does this mean? If they weigh the same amount and we give the same amount of heat source, which one would heat up quicker? Well, that would be your copper pan. However, this works just in reverse. Which one would it take longer for it to cool off? That would be your cast iron skillet. So you can heat up your copper pan quicker, but your cast iron skillet would hold the heat longer. So these things are applicable for, right, everyday life. And let's just note here, so for most metals, well, we have carbon as graphite and carbon as diamond, but we have fairly small specific heats. Notice how large water is. So this tells us that water, one, it takes a lot of energy for it to heat up, so we know how long it can take to boil a pot of water, but it's going to hold the heat for a much longer time. So this is great in terms of in the winter time, right? We know that the top layer of water will freeze. We get ice out on the bay. However, underneath, the water is going to hold its warmth for much longer, which means that, you know, your plants and your fish and stuff aren't going to die. And we just remind ourselves that if we're going to do a temperature change, it is always final minus initial. So practicing with the specific heat equation, a 622 gram piece of copper metal is heated from 20.5 degrees Celsius to 324.3 degrees Celsius. How much heat is absorbed in kilojoules by the metal? So first of all, we just kind of want to pay attention and keep thinking conceptually about things. We see that our temperature has increased. That means that this is an endothermic process. So that tells us that the amount of energy that we calculate has to be positive. All right, some key words, right? It says absorbed. Anytime we see absorbed, that means that it's endothermic. So we identify the fact that here's our mass, here's our temperatures, which we would find the delta T, and then we plug things into our equation. C is our specific heat. You do not have to memorize specific heats. These would be given to you. So we calculate our temperature change, keeping in mind that our final temperature was bigger than our initial temperature because we had to absorb that energy. So we saw an increase in the temperature. This calculates out to 303.8 degrees Celsius, which we know is the same temperature change as 303.8 Kelvin. Do not confuse yourselves in saying that this degrees Celsius is this temperature in Kelvin. That's not what this is saying because we're looking at a temperature change. If we were to convert this to Kelvin by adding 273, if we were to convert this to Kelvin by adding 273, you've added the same amount to both things so that the difference is going to remain the same, once again, because degrees Celsius and Kelvin change by the same amount. 1 degree difference is the same. So we multiply through mass times our specific heat times our temperature change. Grams cancel, Kelvin cancels. We're left with units of joules, which is energy. That's what we want. So 72,751 joules. It asks us to give this energy in kilojoules, so we simply divide by 1,000 or move the decimal point 3 places to the left. And we round for sig figs to 3, so 72.8 kilojoules of heat are absorbed to increase this temperature. How much heat in kilojoules is liberated from 366 grams of mercury when it cools from 77 degrees to 12 degrees Celsius? So once again, we pay attention to our language here. This says it's liberated, which means that it's given off. So we should calculate a negative value of energy because it's exothermic. It says that it's cooling, which means that our final temperature is lower than our initial temperature. So once again, that tells us that heat has to be released. So we calculate our temperature change, keeping in mind that we pay attention that it's supposed to be final minus initial. That gives us negative 65.0 degrees Celsius, which is the same as negative 65.0 Kelvin. We plug things into our equation. Q equals mc delta T. We multiply 366 times 0.139 times negative 65.0, canceling out our units of mass and canceling out our units of temperature. So this tells us that negative 3307 joules of heat had to be given off. We convert that to kilojoules, rounding for sig figs, and see that that is negative 3.31 kilojoules. Within this, Q equals mc delta T, I've shown you 2 equations where we're simply solving for heat. We can also, given the correct information, we could solve for mass if we know what the heat is, the specific heat, and a temperature change. We could also determine what the specific heat is for a particular substance if we were given heat, mass, and temperature change. We could also figure out a temperature change if we were given heat, mass, and specific heat. So we have an equation that has 4 variables. You need to have 3 out of the 4 to solve for the other one.